Moving on with our discussion of EKGs, I would like to talk now about how to detect moving charges, because that's very important to how an EKG will assess the function of the heart. But before we delve into this concept of how to detect moving charges, I would like to do a bit of a recap on some of the concepts covered in the previous two videos about how to detect charge in general. So the first concept that we discussed was how EKGs work, at least at a very high level. And how they work is by detecting charges that are moving around inside the heart. So EKGs work by detecting moving charges, and this concept is key. The second thing that I'd like to remind you guys about is that there's a special kind of sensor that is used to detect the charges, and that sensor is called an electrode. And recall that the electrodes come in pairs, which is the negative electrode and the positive electrode. You can't get one electrode and then expect to be able to detect the moving charges with just one electrode. You need both the negative and the positive electrode. Finally, we talked about how electrodes work. And this is something that I'd like to briefly review again, just in case you haven't, in fact, watched the previous videos. So the key is that electrodes detect charges based on a comparison between what the negative electrode is seeing in terms of charge and what the positive electrode is seeing in terms of charge. And very briefly, I'm going to walk you through what I mean by that. Imagine, and this is all review, that you have two boxes, one with completely balanced charges inside, so they're just as many positives as negatives, and another where there is an imbalance in charge. And we're going to say that our positive electrode is the one we're interested in because we want to see how unbalanced the charges are in the second box. So that is the set of charges we're interested in detecting. So what we would do is use our negative electrode right here as our reference, and we would compare what the positive electrode is seeing to what the negative electrode is seeing. And how we do that is we create a circuit between the two electrodes, and in the middle of the wire is a voltmeter. And how we compare the positive electrode to the negative electrode is we say, if we were to connect our two electrodes by a circuit, what is the propensity of charges to move from the negative electrode to the positive electrode? And now, since there is an imbalance in charge between our box on the left and our box on the right, we are going to actually see some movement of charge between the two electrodes through the voltmeter. And that movement of charge is read out by the voltmeter as a voltage. So that's very well and good. We know that now we can detect charges sitting in a certain place depending on what a positive electrode sees compared to its negative electrode reference. But so far, all the charges we've been talking about have been stationary. They're unbalanced charges that stay in exactly the same place. And what we've always been doing was we've been drawing our box, and then we've been saying, here's our set of positive charges inside of the box. And we have always said, here's our positive electrode, here it sits in our box, and we're now going to compare it to our negative electrode, which is sitting in a neutral solution somewhere else, and that neutral solution is our reference for what the positive electrode is seeing. But the fact of the matter is, these positive charges that our positive electrode was detecting never actually moved with respect to the electrode. The only movement that we ever saw was through the voltmeter. But in cardiology, it's important to detect charges that actually move on their own. That is, say you had another box, and say you have your positive electrode here again, but this time the box is moving around. Maybe this way, maybe this way, maybe this way. But the fact of the matter is our electrode is staying put right here. It's not going anywhere, and our box of charges is careening around all over the place. Now, that kind of activity is what is important to detect in cardiology, because inside the heart, charges are moving around on their own. And it's the pattern of movement of these charges through the heart that is important to how healthy the heart is. And if the pattern is abnormal, that means, or it's a red herring, that there might be something wrong with the heart. And that is why measuring how charges move is so important to our concept of electrocardiograms. So for this reason, I want to talk about how electrodes interpret moving charge. So with that, let's talk about a scenario where we have another box of charges, and I'm going to make our box much longer than before, and you're going to see why in a second. So let's say we have 3 charges sitting in the box. And now let's say, as usual, we're going to put our positive electrode on one side of the box. But now we're going to do something different than we did before. So before, we always put our negative electrode somewhere out in the distance in a completely different solution, and we always made that solution neutral because we wanted the negative electrode to be our reference. Well, this time we're going to do something different. We're going to put our negative electrode on the other side of the box, something like this. And the reason I've set up our box this way is because this is actually pretty similar to the setup in an EKG reading, where we're using electrodes to measure the activity of the heart. So what would happen in that kind of a situation is you'd have your patient sitting in the office, and you want to see how their heart is behaving electrically, and so then, as usual, you're going to place your positive probe on the patient's skin. And even though it's on the skin and not directly in the heart, the electrode can still sense charges that are sitting in the heart. But instead of putting your negative electrode out in a neutral solution somewhere separate from the patient like so, you scratch that, and instead you place that electrode on the patient's skin as well. And so what would happen is that the negative electrode is also detecting electrical activity in the heart, and the positive and the negative electrodes are both on the patient's skin. All right, so bear with that idea for a minute. Now let's say that for some reason the positive charges kind of sit around there for a minute, but then they get bored and they say, you know what, I'm tired of sitting on the left side of the box. Let me go to the right side of the box. And so then they move and they end up here. Okay, now let's assume that, again, as we've always done, our positive electrode is the one that we care about. We want to see what it is seeing. And we're going to call this our test electrode, and we're going to call our negative electrode, as usual, our reference electrode. So what do you think the positive electrode is going to see? Well, this is a harder question because first we've changed how the electrodes are in relation to each other, and second, our charges are moving around. So let me break up this problem for you guys. So I'm going to break down our question by talking about it as if we were looking at 3 different time points. So the first time point would be where we started, where our 3 charges are on the left side of the box. Our second time point is where the charges have now moved to the middle of the box, dead center. And our third time point is where the charges have now ended up on the right side of the box. And again, we have our negative electrode always on the left. We have our positive electrode always on the right. And so now let's kind of predict what we would see at each time point. So at the first time point, which I'm going to call time point number 1, what would you expect to see? Well, we know that the negative electrode and the positive electrode are not seeing the same thing. The positive charges are way on the left, which means that the positive electrode is actually seeing less positivity than the negative electrode. The positive electrode is seeing relatively a negative solution compared to the negative electrode. And so then you might expect that the voltage is somewhere down here. That's where it starts. I'm going to symbolize that with a dot. So at time point number 1, our positive electrode is reading out a negative voltage. All right, now let's move on to the middle frame where we've got time point number 2. And in time point number 2, we're imagining that our positive charges are dead center between the two electrodes. This means that the negative electrode and the positive electrode are seeing exactly the same amount of charge. Well, that means that at a later time point, which is going to be out here, the positive electrode is going to read out no voltage or 0 voltage. Finally, if we go to the last time point on the right, where the positive charges have moved all the way to the right, we're going to see that the positive electrode is seeing much more positivity than the negative electrode. And what that means is you're going to see at a later time point than even in the second one, you're going to see a positive voltage somewhere out here. So if we extended it out to the right time point, we'd see a dot right here. So if you kind of put that all together, the result for our voltage reading is that you would get a change in voltage over time. It starts out here. Later on, the voltage ends up at 0. And then finally, at the last time point, it ends up somewhere up here. And if you connect the dots, you'll get a curve that looks something like this. And when we get a change in voltage, we call that a deflection. And a deflection is basically a departure from a flat line, because recall that in all of our previous diagrams about voltage, we always saw a flat line, meaning that over time the voltage remained constant. But as soon as you see a departure from that flat line, you call that a deflection. And in this case, we're seeing an upward deflection. All right. So now let's engage in some thought experiments about how electrodes detect moving charges. So I'm going to go through 4 important scenarios with you about how charges move with respect to electrodes, and we're going to predict for each one about what we would see on our voltage tracing. All right, for our first scenario, imagine that a positive charge is moving from the left side of the box to the right side of the box, like so. So it's going from the negative electrode to the positive electrode. What do you predict seeing? Well, this is exactly the same scenario that we talked about previously, and we would expect to see a curve that looks like this. And we would call this a positive deflection because the curve moved upwards or towards the positive side of the scale. All right, now let's go to our second scenario. This time, let's pretend that our starting charge is actually negative, and it's also moving from the left side of the box to the right side of the box. So this is basically reverse of what we saw in our first scenario. So the start shows that the negative charge is much closer to the negative electrode and is much farther away from the positive electrode. So the negative electrode is seeing more negativity than the positive electrode. In other words, the positive electrode is seeing more positivity than the negative electrode. So you would expect that your initial voltage would be positive, but eventually the negative charge gets closer to the positive electrode than to the negative one. And so then you'd end up at a negative voltage. So your curve will look something like this, and you would call this a negative deflection. Okay, now let's go to our third scenario, and let's go with a positive charge again, but this time we'll start it on the right side of the box, and we'll have the charge traveling to the left, like so. So now what do you expect? Well, your initial scenario is that the positive charge is closer to the positive electrode than to the negative one. And that means that the positive electrode is seeing more positivity, which means that the voltage would start out positive. But then as the positive charge gets farther and farther away, you'll end up, or the ending point is sort of like the starting point for our scenario right here, scenario number 1. So you're going to imagine that at the end, the voltage that is being read out by the positive electrode is going to be negative. So you're going to have a negative deflection again. Finally, let's start a negative charge on the right side of the box and have it moving to the left. Sort of like our third scenario, except we switched the charge. So again, let's think about this. At the very beginning, the negative charge is closer to the positive electrode. So the positive electrode is seeing more negative than the negative electrode. So you're going to imagine that your voltage is going to start out somewhere here. And at the very end, the negative charge is going to end up right here, close to the negative electrode and farther away from the positive electrode. So you're going to imagine the ending voltage is going to be positive because, let's face it, the positive electrode is seeing more positivity than the negative electrode. So you would expect your positive deflection. So why have I gone to such pains to walk through these 4 scenarios? Well, the reason is that because if you understand these 4 scenarios, you're well on your way to understanding how charges or electrical activity is detected in the heart. Because really, inside the heart, electrical activity can be described by wave fronts of positive charge moving from one side of the heart to the other, or negative charge moving back from that side of the heart to the previous side. And depending on the angle of different electrodes on the patient's skin, the wave fronts could be moving towards the electrodes or away from the electrodes, or at a completely different angle from the way the electrodes are set up. And it's important to realize that there are several combinations of directions and charges that things could be moving around in. All right, so now you guys understand how electrodes detect charges that are moving from one side of a box to another. So let's apply that knowledge now. Let's come up with another scenario that's a little bit different and see how we can interpret that scenario. So let's say we have our box of charges again, but now instead of having the charges moving from the left to the right directly, we're going to instead have them move at an angle like this. So now they're not only moving from left to right, they're also moving from up to down. What will our voltage tracing look like if we're using the positive electrode and trying to get a reading from that? So before we answer this question, let's kind of break things down. What I'm going to do is call this scenario number 2, and I'm going to do 2 other scenarios that might help us solve our problem. I'm going to call the one up here scenario 1, and I'm going to call the one down here or scenario 3. And for each of these other scenarios, we're going to start our positive charges in exactly the same place. And we're going to have our negative electrode on the left, and we're going to have our positive electrode on the right. Okay, so let's go back to scenario 1. And scenario 1 will be pretty similar to what we've already seen before, where our charges are moving directly from left to right. So I've always drawn the direction of motion of charges, or the path the charges are going to be taking, with an arrow. And I've been using this symbol for a reason, actually. And the reason I've used it is because it is very nice at depicting 2 concepts. The first is that the charges are moving from point A to point B, so we can see that there is a distance that these charges are traveling, and the length of the arrow corresponds to the length of the path that the charges are taking. So this arrow is showing a distance. But what the arrow is also very good at showing is a direction that the distance is taking, and that's symbolized by the arrowhead. Now, if any of you have taken physics, you'll kind of see that this is starting to resemble something. What is a distance that also has a direction? If you've guessed vector, then that's exactly right. All a vector is a distance that has some directionality to it. And so we can call the path that our charges are taking a vector. And that's what I'm going to do from now on. Now what we can also do is draw another arrow between the negative and the positive electrode. And what this arrow symbolizes is the path a charge would take if it traveled from the tip of the negative electrode to the tip of the positive electrode. So this blue arrow between the electrodes is another vector. It's just another direction of motion of another set of charges. Theoretical, of course, but it's still very important. And you'll see why in a bit. But for now, just notice that the blue and the black vectors in situation number 1 are parallel to each other. They're running in exactly the same direction, and really the only difference between them is that the blue vector is longer than the black vector. So now let's think about what the voltage tracing would look like for scenario number 1. Well, that's easy. We've already talked about scenario 1, so we already know that our voltage is going to start out negative somewhere over here, and then it's going to end up positive somewhere over here, and we're going to get a positive deflection like so. All right, now let's think of a completely different situation. Let's jump to scenario number 3. And now instead of our charges moving from left to right like so, we're going to actually have them moving up to down like this. So they're going from point A over here to point B down here. And now if we draw another vector between our electrodes like this, we'll see that the black vector, which is the path of the charges, is perpendicular to the path that exists between the electrodes. So this is a 90-degree angle. So what would our voltage tracing look like for this? Actually, our voltage tracing would not change. So if we were to draw our vector again in green, we would again say that our voltage would start out somewhere here, but as the charges move from this part of the box to this part of the box, the difference that the positive electrode is seeing compared to the negative electrode is pretty negligible. The difference doesn't change. And so you're going to see a voltage somewhere out here, and it's going to be a horizontal line. Now, why is this so? Let's say for a moment that we cleaned up our diagram. If we were to draw a line up and down like this so that it's at right angles to our blue vector, a charge that sits along any point of this line will read out exactly the same voltage. So as long as a charge moves up and down this line, the voltage is not going to change. All right, now let's go back to scenario number 2, which was our scenario of interest, which is where our vector, the path that the charges are moving, is taking on an angle compared to the path between the electrodes, which is our blue vector right here. So how is the voltage readout going to be different? Well, we know already that it's going to start out here. All we have to figure out is what the reading will be when it ends up somewhere here. Now, a key assumption that I'm going to make is that the yellow vector right here in diagram number 2 is exactly the same length as the black vector up here in diagram number 1. And I know the diagram isn't to scale, so I apologize for that. But we're just going to pretend, for this instance, that our yellow vector is the same length as the black vector. And what that means is that the charges that are moving from here to here are moving the exact same distance as the charges in this diagram, which are moving from here to here. So why is this important? Well, it's important because in scenario number 2, the charges are moving exactly the same distance as the charges in scenario number 1, but some of that distance is devoted to going up and down, which, as we've already shown in scenario number 3, doesn't make a difference to the relative difference between voltage that we're going to see, or the relative difference in charge that the two electrodes are seeing. The only component of motion that matters is that component that runs in this direction, which is parallel to our blue vector. If we were to break down the yellow vector into its respective components, which are up and down and left and right, we would find that this left and right component is shorter than the yellow vector itself, which means that instead of ending up somewhere out here, like what we saw before, the charges are going to end up somewhere out here instead, along this black line, which means that although the charges end up closer to the positive electrode than to the negative electrode in the end, they don't end up as close as they could have if the vector had been moving directly from left to right. It means that in the end, our voltage is going to end up perhaps not so high or not so positive, and that would mean that our deflection would look like this, and it would stop short at a lower voltage. the result is that the larger the angle between the vector that symbolizes the path of the charges and the vector that goes between the electrodes, the lower the magnitude of the deflection. Okay, so what concepts have we covered so far? The first is that electrodes detect moving charges as deflections on the voltage tracing, that is, as changes in voltage. The second thing we've learned is that the path that charges take from one side of a box to another, or even from one side of the heart to the other, can be called a vector, which, as you recall, is a distance that has direction. And the final thing that we learned is that the magnitude of deflection that is caused when a charge moves depends on how the path the charge takes, how well that coincides with the path that sits between the electrodes. A more formal way of saying this is that the magnitude of deflection depends on the projection of the charge motion vector onto the vector that sits between the electrodes. What I mean by projection is the part of the charge motion vector that is parallel to the vector between the electrodes.